Yeah, that is indeed correct, at least the second part. Anyway, thanks a lot, Ludovico. Yeah, so there's this long technical title. I would like to replace it with not necessarily simpler, but shorter. I will talk about matrix analysis methods to prove quantum entropy inequalities. And yeah, I have to apologize. I will not talk about applications of these inequalities. I will just talk about kind of the mathematics behind them. But let me assure you, there are lots of applications. Yeah, check out the paper or also talk to me later. The second thing is I don't have many references. There are just too many. But again, just talk to me afterwards. Good. So we want to talk about entropy, so we should quickly define what we mean, and I would like to start classically, right? So if we have a probability distribution of many parts, okay, label them A, B, C, for example, we can define this well-known Shannon entropy, and then we can, when we have multipartite systems, yeah, we can start defining correlation measures that are based on the entropy function, right? So for example, we can define this mutual information, which is kind of the interpretation is how much two random variables have in common. We can define entropy, okay, so how much uncertainty you have about A if you know B already. And you can also combine these two measures, and I'm sure many of you have seen this, so I'm going through it quite quickly. You can define this conditional mutual information, which is supposed to quantify how much A and B have in common if you know C already. Another point about entropy inequalities, or one type of linear entropy inequalities, is all this greater or equal to 0 that you can see here. So in some sense, this actually justifies these definitions. Okay, so this is kind of the textbook landscape. Let me tell you that even in a classical setting, quite funky things can happen, and these inequalities are called non-Shannon type inequalities. So you have these linear inequalities that take this very weird form, but one can prove that they're independent of these other inequalities. So there are actually infinitely many of these non-standard inequalities as well. But this is more of a side remark, because of course I would like to talk quantum, right? And here we have the von Neumann entropy, which is usual definitions for quantum states or multipartite quantum states. And then we can try to define the same measures as we did classically. And then for the mutual information, everything's fine. Like this thing stays non-negative, all good. If we go to the conditional entropy, one can easily see that this thing can become negative, right? So for example, if we look at a bipartite maximal entangled state, it's a pure state, so this entropy will be 0, and this thing will just be minus the log of the dimension of the B's instance. So this is not necessarily a problem, but this is a behavior that is different from the classical behavior. And then interestingly, if we define a quantity that combines these two measures, again, this conditional mutual information, one can still prove that this is non-negative. Okay, so this is called strong subjectivity. It's a very famous statement. And there's actually a reformulation of it that is equivalent to this conditional mutual information non-zero non-negative statement, and it's sometimes called weak monotonicity, but what I would like to argue is that this strong subjectivity statement is a statement about monogamy of quantum correlations, and we saw that in a few of the previous talks this afternoon already, and the weak monotonicity statement is here. So if you have a tripartite state, right, rho ABC, then each of these conditional entropies, they can become negative, because if the state is very entangled, between A and C, for example, a state will, the entropy will be negative. However, if you add these two conditional entropies of this tripartite state, it's again a non-negative. Okay, so that means if one state is very entangled between, let's say, A and C, then it cannot be entangled very much between A and B. Okay, so it's really a monogamy of entanglement, and in that sense, whenever you can extend classical to quantum entropy inequalities, then this tells you a lot about the entanglement spectrum of quantum states, right? Namely, it gives you a restriction of what type of correlations are allowed. Good, and yeah, so from this introduction, you can see, okay, today I want to present some tools or a recipe how to prove quantum entropy inequalities, and I would like to do it directly with a matrix analysis approach, because often we have kind of contrived proofs that uses a lot of like quantum information language, but actually if you just look at the mathematics behind these functions, you can get very neat and simple tight proofs, I would argue. Good. Now we could look at all kinds of entropy inequalities as an example. I would like to look at strong subjectivity, but now not just the bare version, but some refined versions of it. Okay, so let me first tell you how these refined versions look like in the classical setting. Now, in the classical setting, there is this relative entropy, also a Kullback-Leibler divergence. I'm sure many of you have seen this measure as well. And then one can, in an elementary fashion, see that one can rewrite this condition mutual information as a relative entropy distance here, okay, of the original state, P, A, B, C, to this state over here. So now what is this? Well, so the PAC is just the reduced state on the AC systems, right? So if you look at this picture here, you have AC. And then the QBC is any conditional probability distribution, or in other words, a channel, as they would say in the quantum setting. So this is applied. So I am dropping here an identity on A, as I will do for the rest of the talk. But this is a channel that only applies on C and recovers this B state. Okay, and one can minimize over those and then exactly gets the condition mutual information. And okay, the optimizer is also just achieved on this combination of marginal states. Good, so what does that tell us? Well, first of all, it tells us, because we know that the relative entropy is non-negative, this actually proves strong subadditivity classically. But second of all, it also tells us that if we have a distribution, right, that has small condition mutual information, then it actually has to be close to a state that is locally recovered, so to speak, right? Like a general state will not have this form that you can recover the B just from the C, but these particular states do have that. So this is kind of what people maybe would call a recoverability refinement of strong subadditivity. And now there's a kind of a trivial reformulation again of that, where you just understand the second argument here as a Markov chain, where the conditioning system is the one in the middle, so it's the C system. So here then the statement is that the conditional mutual information, it's equal to the relative entropy distance of your state to the next Markov chain. Okay, and again, the optimizer is achieved on this combination of reduced states. Good, and so one more thing you can immediately learn from this is you can get the equality conditions when this condition mutual information is equal to 0, right? Because we know the relative entropy is 0 if and only if the arguments here are the same, then we know that, okay, whenever the condition mutual information is 0, then we have either a locally recovered state, or equivalently, we know the state is already a Markov state. Okay, so these are these kind of strong subadditivity refinement that are quite easy to get in the classical case, but of course in the quantum case a little more work is required. Good, so yeah, let's talk about that. Now to do that, probably I should first tell you again about this parent quantity. So classically we had this Kullback-Leibler divergence. Now if you go to the quantum or non-commutative setting, this extension is of course not unique, right? I think the measure that most of you have seen probably is this quantum relative entropy, or Umegaki relative entropy, which takes this form. But in principle we could also define other measures that then on classical states would again simplify to this Kullback-Leibler divergence. So one measure that got recently a bit more attention is this so-called geometric relative entropy, which takes this form, and then you can check that if rho and sigma commute, yeah, this all become the same function. Another one that is of some interest is the so-called measured relative entropy. So here the idea is you just take the states rho and sigma, and you apply a measurement, and then on the post-measurement statistics, you just you apply the classical Kullback-Leibler divergence. And then you want to take the best possible measurements, and this also defines a valid non-commutative generalization of your classical relative entropy. Good, so these are actually all good definitions, and they are ordered, and in some sense, this geometric one is the largest one that has reasonable properties, whereas this measured one is the smallest one that has reasonable properties. So now if you want to generalize classical things, right? Whenever you're looking for upper bounds, you might want to work with this geometric one. If you're looking for lower bounds, you might want to work with this measured one. Good. Now there's actually even more such measures. Namely, if you have multipartite states, okay, then what you can do is instead of just taking a general measurement in this measured relative entropy, you can restrict your measurement that you apply to certain classes, right? So for example, you can only look at local measurements if you have a bipartite system, or you can only allow this local operation, classical communication type of measures. You can look at separable measures, PPT, whatever you like, basically. And then you define in the same way as before, right? You just take your states. Now they have to be at least bipartite. You apply your measurements, and now the measurements have this structure. And then on the post-measurement states, you apply the classical Kullbaum-Leibler divergence. Good. So again, these things have reasonably nice properties, and of course they're ordered, right? The bigger you take your set, the bigger is the set you take the supremum over here. And so you have this ordering relation. They're also all non-negative. And now if you choose a reasonable set M here, namely one that has informationally complete measurements in it, you also get these equality conditions again. So in particular for all of these possible sets of measurements, you do have these equality conditions as well. Good, and again, if you start with classical distributions, right, all of these quantities will become the same. So we have these families now of non-commutative generalizations of the classical measures. And the point is now, if you want to generalize classical to quantum entropy inequalities, you have to choose the right measure here, such that you can actually prove stuff, okay? Good. Now let's come to the first generalization in terms of these recoverability bounds. So remember, we wanted to think of this as a relative entropy distance to this next locally recoverable state. So this was the picture here again, right? Now the problem is if you work in a quantum setting, you can do a similar thing, but then you have this exponential operator here. And since these are all matrices now, you cannot just split this up as you could do in the classical case. Yeah? So it's not really clear where to go from here. However, I think Petz already in the 80s was able to show that one can actually show these equality conditions. Condition mutual information is 0, if and only if the state is of this locally recovered form. Okay, so the R is just a quantum channel now. So this is the exact analog to the classical result. But then classically we had more, right? Namely we knew that condition mutual information was equal to this relative entropy distance here. But unfortunately this is not true, like in this form. This has been known for a long time. But then given my story today, right, the problem is just we chose wrong quantum generalization here on the right-hand side. So one can actually show that if one uses the measured relative entropy, which is in general potentially smaller, yeah, this bound actually holds. It's no longer an equality as it is classically, but one still has this lower bound, which is often what one wants. And yeah, this was presented at QIP, and there were lots of follow-up papers. And one I would like to mention in particular is one can actually find very neat, again, matrix analysis-based proofs of this statement. Okay, we'll get back to this in a minute. Good, so we're kind of happy about this statement. So I'd like to go to the second quantum generalization, namely if we want to talk about this quantum Markov state or the classical Markov state version, and then in the quantum setting, right? Good, so again here, Petz and collaborators, I think in the 90s, they found an equality condition that is phrased in terms of a kind of a Markov off-chain condition, namely the condition mutual information is 0 if and only if there exists direct sum decomposition of the C system. Okay, the C system is the one we condition on. And then the state takes this form. Okay, so now you can see, and that if you know C, right, then A and B are in that sense like independent. Okay, so this is the mathematical formulation. And of course, okay, these are the equality conditions. So we might again ask, as many people did. I think Andreas Winter was first. Can we prove statements like this? Okay. But now again, we have a no-go result, and now it's not even enough if we go to this measured relative entropy, unfortunately. And there's actually a relaxation that is also of great interest in entanglement theory, namely if we trace out the C system, this right-hand side will only become smaller. And this is still an interesting statement, because you see if you look at the quantum Markov state like this, if you trace out the C system, the resulting state will actually be separable, so it will only have classical correlations. Unfortunately, this is again not true, and the solution here is that we have to go down a little further, namely we also have to restrict the measurement, the test operators here to a smaller set. So this is this one-way LOCC set. But then this can be proven again. Okay, so this tells you if the conditional utilization is small, then your state is close to a separable state in this type of distance measure. So now, in the remaining few minutes, I would like to briefly sketch how one arrives at statements like this in a direct fashion. Yeah, because should maybe also say that this original proof of these guys, this was also using this generalized quantum standardized Stein's lemma that we don't know to hold. So at least the version that is online at the moment, there's like a gap in the proof if you want. But I think, yeah, it's a fixable gap in this case. Good. So let me briefly talk about the proof techniques. Hopefully I convinced you that this is interesting enough. Yeah, so there are two ingredients basically. One are trace inequalities, or in particular multivariate trace inequalities. Multivariate because we have multipartite quantum systems. So if we look at all the possible reduced states, these are matrices, and if we have multiple states, we have multiple such matrices, and they're of course non-commuting. Now, what is a trace inequality? So the most famous example, I think, is a Golden-Thomson inequality. So this just tells you, like, if you take the exponential of a sum of matrices, like in general, this is not related to the product of the matrices, as long as the matrices don't commute, okay? But if you put a trace around it, you can still get this upper bound. This is quite a non-trivial statement, but now we need actually the generalization of this where we have n matrices, okay? So yeah, this PowerPoint formatting is not great, but so basically you have an exponential of a sum of n matrices, okay? And you want to upper bound it with something that is the product of the individual exponentials. And you can do so if you rotate all of these matrices a little bit, and then you average over some universal probability distribution. Okay, and this really tells you how these different matrices kind of interact. Okay, so here they're all together, here they're all separate. This is an important tool, and actually this should be 2017, but this direct matrix analysis proof used this, derived this extension for the first time. Good, so this is the one ingredient, right? This trace inequality that tells you how all these matrices of the reduced state interact with each other. And then the second ingredient are these variational representations of entropy. So this is a classical formula that holds for the relative entropy. And so you have to optimize here over some operator W. And you see in this optimization, like you have the P and the Q dependence kind of disentangled from each other. So you have different terms, and one can derive quantum analogs of this. So this is also a well-known formula by Petz. So if you look at the relative entropy, you can write it in this fashion. Similarly, you can write these measured relative entropies in this even simpler fashion. And you can already see here, to go from here to here, you exactly use a Golden-Thomson inequality, yeah, for two matrices. Yeah. Good, and now what is new in our work is that we now also derive such variational formulas for the measured relative entropy when we restrict the measurement to certain sets, okay? So, okay, technically one has to look at this CM quantity, but so for example, if we put here a separable, then you just have to optimize here over separable operators. Okay, in general, it's only an inequality. For some sets, it's also an equality, but this is a new ingredient that we now also have these variational formulas for these locally measured quantities. Good. And now I don't think I will have time to actually show the proof, but what we show is a more general statement of this lower bound that I promised before. Okay, here this just uses the shorthand notation where we have the relative entropy of entanglement that we also saw in previous talks. And if you have this more general inequality here, then you can deduce as a corollary immediately this lower bound. So the blue thing here is the previously known inequality. And what you do is you just evaluate this green statement on the n-fold tensor product state, and then this last term here on the right-hand side falls away. And first you get this regularized quantity here, which you then can again lower bound further. Good. I think I will skip now the proof sketch because I'm basically at the end of my time. But really what you do is you use these two ingredients in a very basic fashion. Let me skip this. Okay, some long formulas. And so what you can get from these formulas is also that here on the right-hand side, right, we had this bit weird-looking set where you look at these LOCC1 measurements. But from the proof, you can really see that you need exactly this structure to derive this lower bound. And I would like to emphasize that basically the only inequality that you use is this Golden-Thompson inequality, in particular the 5-matrix Golden-Thompson inequality. So this is where you kind of control the non-commutative effects. Good. Yeah, you can do a lot of other stuff with it. So please look at the paper. So basically the condition information is a tripartite measure. You can go to 4-party measures. You can go to multipartite measures, and you can do similar kind of tricks. Okay, so this is just kind of a technique. And I hope I convinced you that this can be useful. Good. What are the conclusions? Well, we prove entropy inequalities that did hold in the classical case. Now they also hold in the quantum case, and this tells us a lot about the structure of multipartite quantum states. And what did we use? Well, it was important to realize that these locally measured quantum relative entropies are there, and that we can use them as well as a possible non-commutative extension of the classical relative entropy. We have these variational formulas, and we have multivariate trace inequalities. Good. I think I leave it at that. There are lots of open problems, and these are some of the talks I find interesting that are still to come. Okay? It's probably an incomplete list. Good. Thank you.
Thanks, Mario, for the great talk and wonderful insights into entanglement theory. Any questions?
Thanks for the nice talk. So you talked about this separability where you can relax the set of the measurements to this one-way LOCC, and then you have the lower bound for the conditional mutual information. Is there any results from your work about the actual quantum Markov chain states?
And there's not. We tried, but okay, I have to go quite a bit back. But basically, you could conjecture a similar thing, right? You could just say, okay, why do we trace out the C system? Just leave it in there, go to the next Markov state distance, and then prove the lower bound. So there are no known counterexamples to that. So all the no-go results would still be allowed, yeah. So if you have any ideas, that would be great, yeah. I mean, that was actually the original goal of all of this, but we fell short, I guess. Yeah.
Any other questions? Which relative entropy would you use for the full tripartite case?
Well, that's open, right? But okay.
Yeah, exactly.
So I have to go back a bit.
Yeah, go.
Sorry about that. Yeah, okay, it's a bit slow. Well, you could use either. Like you could, for example, just use local operations on A, B, and C. Or you could do something where you measure on A and then send to C and measure on B and send to C. I don't know. Like, I mean, any set that includes informationally complete measurements, I think, would make.
I guess the message from your talk is that you need some of this locally measured relative entropies. So you need that tripartite.
Yes, that. But then it might still be possible to do, right? Like kind of this twofold message. Yeah.